Okay, guys, so in 9.1 and 9.3, we're going to talk about differential equations. We're going to skip 9.2. I'm going to kind of pick my battles. I don't have a perfect way to teach that right now through online teaching. So we're going to kind of focus on the important stuff. Not to say that's not important, but it is something that at other schools we do skip that topic. So 9.1 differential equations. So this is just kind of an intro to explain what differential equations are. So we're going to be working with differential equations, and they relate the rate of change of a function, which we know as the derivative, and higher order derivatives of a function to the function itself. Okay, so you're going to have a derivative, maybe a second derivative, maybe a third derivative. And you're then going to also have those derivatives related to the original function as well, say f of x or h of x or whatever the case may be. Okay. So one thing when you're dealing with differential equations is you like to classify them. So we're going to classify differential equations by order. Okay, so you have a first order, a second order, a third order differential equation. And what that means is it is the highest derivative that is present in the problem, okay? So whatever you're working with, you're gonna classify it by the order. Now, again, I'm not gonna ask you a test question, per se on what's the order of the differential equation, because you could just look at it. But an example of this would be, suppose you had y double prime minus 2y prime plus 6y is equal to 0. Okay, so this would be what? This is the biggest derivative in this, the highest degree derivative. I should say the highest order is second. So this is a second order differential equation. Okay, so let's look at another example. So we have dy dx minus 5y equals 1. So this would be a first order differential equation. Let's look at just one more. And again, if you're wondering, remember dy dx is just the first derivative. If it was d squared y dx squared, then it would be a second order differential equation. Now we have x plus y minus 4y dy dx equals 0. So once again, this is a first order differential equation. So that's when we're discussing order, that's all it's saying is what's the highest derivative present in the problem you're working with, okay? Now, something that is very important for differential equations is to understand what a differential equation is. Understand what a solution to a differential equation looks like. So it's very important you guys understand a solution to a differential equations is a little bit different than what we're used to seeing. You know what? I'm just going to start writing differential equation. Okay. Is a function. A solution to a differential equation is actually a function. Okay, that when substituted in to a differential equation, it creates an identity or produces an identity. So let's see what that means. Okay, so an example. You might be asked, is y equals e to the x squared a solution to the first order differential equation dy dx minus 2xy equals 0. We want to know if this is a solution. Okay. Now, normally when you're working with problems and somebody asks you for a solution, you end up getting like x equals 5 or, y equals 2. But remember, we're working with differential equations. So the solutions to differential equations are functions themselves. So they're saying in this problem that y equals x squared, that's the solution that they want us to check. They're saying that's our actual answer. And the way we check it is we plug it into the differential equation. So I'm going to take this guy and bring this whole problem over here. So we have, dy dx minus 2xy is equal to 0. Okay. Now, what I need to do is I need to plug in y equals x squared for y. Well, that'll be great for right here. But what the heck am I going to plug in for dy dx? Well, all I got to do is find dy dx. Okay, so I'm going to say that y prime, or dy dx, let me make this a little bit finer, dy dx can be found by just taking the derivative dy dx of both sides, and we'd get 2x e to the x squared. If I take the derivative of e to the x squared, right? It's e to the u times u prime. So this can now go and plug in right there. So now let's see what we get when we write all this out. We're going to get 2x e to the x squared minus 2x times y, but what's y? Y is e to the x squared, and that's supposed to equal 0. Well, 2x e to the x squared minus 2x e to the x squared is 0 equals 0. This is an identity. So yes, it is a solution. Okay, does that make sense? That's what they mean by an identity, all right, is that you're going to take the problem and you're going to plug it in, you're going to take your value for y and you're going to plug it into the differential equation. If it creates an identity, then you're good. And you say, yes, it was a solution. If it doesn't create an identity, then it wasn't a solution. It's pretty simple, okay? Let's take a look at another one. Example 2. Is y equal to x a solution to y prime plus y double prime equals 3? Well, that means that if y is equal to x, then y prime is equal to 1 and y double prime is equal to 0. So we're going to plug this in right here. We're going to say, well, let me do it in green real quick. So y prime is 1 plus 0 equals 3. So 1 equals 3. That is not true. So no, not a solution. So y equals x is not a solution. So this is not a solution to the differential equation. Okay. So let's look at this one. Y equals x e to the x. Let's write example 3. Let's do this as our third example. So I want you to do the same thing. I want you to find if y equals x e to the x is a solution to y double prime minus 2y prime plus y equals 0. So that means when we plug all these values in, we should get an identity. So 0 equals to 0. But in order to get started, we have to first say, well, if y equals x e to the x, then y prime is equal to e to the x plus x e to the x. That's just the product rule, right? And then y double prime is equal to e to the x plus e to the x plus x e to the x. Double check my work on that, but hopefully we're good. So this becomes 2e to the x plus x e to the x. Okay. So now let's plug it in green. So y double prime is 2 e to the x plus x e to the x, that's this guy right here, minus 2 times y prime, but that's e to the x plus x e to the x, right? Plus y, but y is x e to the x, that's this guy right here, and all of that should be 0. So now let's clean this up. 2 e to the x minus 2 e to the x minus 2x e to the x plus x e to the x equals 0. All right, so let's see what we got left. So we got 2e to the x negative and positive 2e to the x, okay? Then we have x e to the x and another x e to the x. That would be 2x e to the x. And here's a minus 2x e to the x. So they cancel, and they cancel. And we get 0. So we end up with 0. Oops. We end up with 0 equals to 0. Check. So yes, y equals x e to the x is a solution. Okay, so this is how you can check and verify if something is a solution to a differential equation. In the later sections in 9.3 and 9.5, we're going to actually figure out how to find these solutions. But for now, we're just verifying a little bit to see if they are in fact solutions to the differential equations. Okay, so let's look up here a little bit. So now it says, example 4, for what non-zero values of C is y equal sine C of t a solution to y double prime plus 4y equals 0. Okay, so take a minute, think about what this is saying. For what non-zero values of C is y equals sine ct or sine of ct a solution to y double prime plus 4y equals 0. Sorry, I was reading something else. Okay, so what do we need to do first? In all of these problems, what's the first thing you have to do? What I would do is in general is just kind of write out what I have to start. So sine c of t, that's my y. Y prime is cosine ct times c, right? The chain rule. Then y double prime is equal to, let's see, negative c sine ct times another c. So this should give us negative c squared sine c of t. So I just keep doing the chain rule. And if I had y triple prime, we'd go back to cosine, and then we'd have c cubed and so on and so on. But I only need to go up to y double prime because that's all that is in the problem. Okay, the highest order is, or the order of the differential equations is 2. It's a second order. So I'm just going to plug in what I found. So I found that y double prime is negative c squared sine ct plus 4 times y, but we know that y is sine ct. That has to equal 0. Okay. So let's see here. We have what in common? Looks like we have sine ct in common, so I'm going to factor that out. So we have sine ct, or sine of ct, times negative c squared plus 4 equals 0. So I could just rewrite this a little bit cleaner. Ct, and then we could do negative, throw the negative back out there. Oh no, you know what I want to do? Let's do this. Let's just do 4 minus c squared equals 0. Now, here's the thing. When we look at this, so it says that sine c of t, this guy's a little bit of a problem for me. Sine c of t oscillates, so I can't promise you all the times that it'll be 0. So it's really tough to deal with oscillating because sometimes it will, sometimes it won't. And I don't really want to mess with that. However, or the way it's worded, there might be another sine or cosine problem that the oscillation we could manage. But right here, it's not really something that we're going to deal with. However, here we could take 4 minus c squared, let it equal to 0. We have 4 is equal to c squared, so c is equal to plus or minus 2. Okay. Now, some people, might say, well, what if c was 0, right? And then it doesn't matter what t is. You guys understand the problem with this one is if we try to solve for c, we also don't know t. So t and c are combined, one could be one and one could be the other, and it could mess everything up and it could keep causing oscillation. But you might say, well, what if c was 0? Then it really doesn't matter what t is. So you might be hesitant and say, well, c should be 0. That should be one of the values. But remember, the original problem said for what non-zero values of c. So yes, that one would work, but they don't want that one. That one's kind of like the obvious one. They want to find the others, and that would be plus or minus 2. Okay. So the only way for this equation to be guaranteed to always be 0, no matter what, is if c is plus or minus 2. Now, there might be other situations that maybe it would be 0 with the sine ct, but you can't promise me all of the infinite choices. So what we're going to go with is plus or minus 2. And again, 0 is technically another one, but they specifically said we don't want that. Okay. So the only way for this equation to always be 0 is to have 4 minus c squared equals 0, which means that c has to be plus or minus 2. So we found what it needed to be in order to guarantee that it'll be a solution to this differential equation, or that these c values could guarantee that y equals sine c of t would be a solution. Okay, so that means you could plug these two guys in right there, and you could plug this guy in right there, and you should be good. Okay, so now let's take a look at something slightly different. Okay, so I'm going to draw you guys a little picture, and I want to see what these look like graphically. Okay, so we have this, and I'm just going to draw a little thing right in the middle, right there, a little axis. Okay, so this is 0, and I want to know the solution to 1, or let me put it this way. This graph represents the solution to 1 of the differential equations listed below. So I'm going to give you guys 3 differential equations, okay? And I want to know which one of them. So we'll call this first one differential equation A, and this is y prime equals xy. I want to know which one of these guys this graph represents, okay? Then we're going to have B, differential equation B would be y prime is equal to 1 minus 2xy. And then we're going to have C is equal to y prime equals negative 2xy. Okay, so something you notice is that it's a differential equation. It's taking the derivative and relating it to the function and the function itself, y. So something you have to kind of think about when doing this is what looks like one of the most important spots, what looks like one of the most important locations on this graph. Well, I would say somewhere right here. Right here. You guys remember that if we drew a tangent line right there, we would get a slope of 0. Okay, so now think of this. Each one of these graphs, this guy, and this guy, I'm sorry, each one of these differential equations is saying that y prime equals. But remember, doesn't y prime stand for the slope of the tangent line? So our slope of our tangent line at 0, and remember, that's our location right here, 0. If we look up, we're at 0, right? So if we look up there, we're at 0. So the slope of my tangent line at 0 should be 0, okay? So let's look at part A. Let's look at our differential equation A. So if we look at differential equation A, what's my x value? Okay, I don't know my y value, I don't know my height, but I know my x value is 0. Okay, so if I plug 0 in right here, what would y prime equal? Y prime would equal 0. That's a win. That's a good thing, right? If I plug 0 in right here for x, I have y prime is equal to 1, right? So if this becomes 0 right here, if x becomes 0, that'd be -2 times 0 times y, which would be 0. And then we have our 1 minus 0 is just 1. Well, that's no good, so it can't be this one, right? So we know b is thrown out, okay? Does that make sense to everyone? That if I plug 0 in for my x value, I get a slope of 1. And right here, the slope is obviously not 1, so that can't be it. So let me clean this up a little bit. So we have y prime equals 1. Now we come over here, and if I let this guy right here be 0, then y prime is equal to 0 still. So far it's looking like it's either A or C, right? So now we have to think again. Okay, now let's go again. Now, what about over here? What if I drew a tangent line right there? Okay, what type of slope is that? Is that a positive slope or is that a negative slope? And again, we don't know actual numbers, but I know that's a negative. I mean, I know that's a decreasing slope. That's negative, right? So what I'm going to do is I'm going to guess, and I'm going to say, what's my x value? I don't know, but it's some positive number. So imagine if we're right here, and let me, you know what? Let me erase this a little. Oops. Let me draw it in a different color for you guys. So if we draw our tangent line right there, and this is the value we're looking at, okay? Now think about that. My tangent line there, my x value is positive. What's my y value? In that location, my y value is also positive. How can we say this? My x value is positive, my y value is positive, okay? So that means when I plug it into my derivative formula, I better be able to get a negative slope by plugging in two positive x and y values. So let's look over here now. Oops. Let's look right here. If I plug a positive in here and I plug a positive in here, a positive times a positive is positive. You're telling me that if you plug two positives into this differential equation for x and y, you would get a positive out. Well, that's not good, because what are we supposed to get? We're supposed to get that y prime is equal to a negative slope, okay? So then we got to go over here. So this one can't be it. I now know it can't be that one either. So now let's look at this guy a little. Now, obviously, you guys know from elimination it's going to be C, but let's just double check. Y prime -2 times a positive x times a positive y. And again, we don't know what they are. We don't care. We know that we're going to get a -2 point something. Or let's just write this. We know we're going to get a negative slope. And that's what we needed. So if you plug a positive x and a positive y into here, you will get a negative slope, which is the type of slope we get here. Now let's just double check. What if we came over here and we drew a tangent line, say right here somewhere? So in this case, my x is negative and my y is positive. So let's test and see if C still makes sense. Y prime equals -2 times x is negative, y is positive. Now we see y prime is equal to what type of slope? Well, a negative and a negative is a positive times another positive is a positive. So we should get a positive slope. And if we look over here, that is a positive slope, right? So as you guys can see, it has to be C. C is the only differential equations that has a chance of being true with this problem. Okay, so this is a way that you can kind of think about differential equations and their graphs. Okay, So that's kind of an intro to differential equations. I kind of want to talk to you guys now about 9.3, okay? So I'm going to get you guys started on 9.3. Let me go back real quick. Yeah, let's just keep going from here because that was kind of a short section. You know what? Let's create a new one. Let's add a page, okay? And let's call this 9.3, okay? So 9.3 is going to be separable differential equations. So this will feel a little bit better to you guys. I think this will feel nicer. We're going to skip Euler's method for now. That's in 9.2. If we have time at the end of the semester, I'll come back to it. But for now, I want to really focus on things that are easier for me to teach online without like asking live questions with you guys. So we're going to talk about separable differential equations. So for many of you, you guys will like this much better than some of the other stuff we've been working with. Separable differential equations will feel very concrete. It'll feel very nice. You'll enjoy them. They'll make sense to you. So a separable differential equation, is one that can be written in this form. And it's going to be h of y equals g of x dx. And don't get too carried away with that. That's just showing you that some function in or something based on y can be moved to the same side as d of y, okay, or dy. So something we can look at is we can say determine if the following are separable differential equations. So determine if the following, that's pretty, sorry about that, you guys. Following are separable. Okay, so first one we have x dy dx, and we're going to use Leibniz notation almost exclusively in this section. So whenever it's not written with Leibniz notation, you fix it and write it with Leibniz notation. In general, that's how we want to do it. So can this x dy dx equals y cubed be turned into the form above? So all we do is we come over here and let's see here. We have to remember the whole point is at some point or at some moment we're going to be asked to integrate these to find the solutions. So you never want your dy or dx in the denominator. So we're going to have to multiply the dx over to the other side. So that'll leave us with x dy is equal to y cubed dx. Now, what you can do is you can divide both sides by y cubed. And that'll leave us with, and I'm not gonna write it out, you guys, but I guess I will. I'm gonna divide x here and divide x here. So this x will cancel this x. This y cubed will cancel this y cubed. And we will be left with dy over y cubed equals dx over x. So basically they want to know if you can get the dy's on one side and the dx on the other side and make sure they're both in the numerator. That's the big deal. The dy and the dx can never be in your denominator. As long as you can get all the x's with the dx's and all the y's with the dy's or whatever variables you're working with on two different sides, then you're good, okay? Let's look at another one. Oops. We have cosine of x plus cosine of y is equal to dy dx. I will tell you guys that a lot of times that cosines and sines and tangents and trig functions in general and inverse trig functions, when they have variables separate variables inside each one of the trig functions, a lot of times you're going to run into trouble, and you may need some other type of method to deal with differential equations in that case. So if I multiply dx over to the other side, that means that the cosine of y will also get a dx. So this actually will not, this is not separable. This is not a separable differential equation, because the moment I multiply that dx over to the other side, I'm in trouble. So that it's normally pretty obvious when you can't do it. This one will be y sine of x minus y x e to the x equals dy. Okay, so let's see here. Let me multiply the dx over to the other side. Okay, so this will be dx y cosine x minus dx y e to the x equals dy. So this is looking very terrible. However, I notice that both of them have a y in common, so I'm going to factor out a y. That would leave me with dx, dx cosine x minus dx e to the x equals dy. I'm going to divide both sides by y. So I now have dx. Now they both, the left-hand side, so this is gone and this is gone. And the left-hand side both have dx's in common. So I guess I could have done this from the beginning. Yeah, I could have factored out the y from the beginning. I didn't need to distribute the dx. That's my fault. And then we have cosine x minus e to the x equals dy over y. It's not erasing. Dy over y. Yep. Oops, I think I lost something in there. I lost this x. I'm sorry, guys. That x, I just forgot to write it. That was just a brain typo. So we have dx x e to the x. So there should be an x here. Sorry about that, you guys. But yeah, it should be cosine x minus x e to the x times dx equals dy over y. So we did separate it. We got the dy and the dx in the numerator, and we got all the x's on one side and all the y's on the other. Okay, and we got them to go along with each other. So this is what it means to be separable. Okay, so the reason we do this is we want to find a solution to the differential equation. So you remember in 9.1, I was already telling you the solutions and I was asking you to verify them, okay, to verify if they were. What we're trying to do is we're trying to find for a solution ourselves, okay, or a general form or a family of solutions. So what we're going to do is we're going to say find solution to x dy dx equals y cubed. Okay, so first of all, we want to know if this is separable. Well, let's see here. I could get and rewrite it like this. I could rewrite it as x over dx times dy equals y cubed. And now remember, you might want to do this right off the bat. You might say, oh, you know, let me divide both sides by dy to get the dy's on the same side. But that's, remember, that's 100% illegal because dy cannot be in the denominator. Right? So what we're going to have to do is we're actually going to divide both sides by y cubed. And then we're going to multiply this side by dx over x and this side by dx over x. So if you notice, once again, this will cancel with this will cancel with this, and this will cancel with this, the y cubes will cancel, and we'll be left with dy over y cubed equals dx over x. Okay. Now, what we're going to do from here is we're going to try to find a solution to our differential equation. And remember, solution to a differential equation, a solution to the differential equation that was listed up here. So here's our differential equation, okay? A solution to the differential equation is another function itself. So we shouldn't be expecting to get some nice clean answer, okay? So what I'm gonna do is I'm gonna integrate both sides to get rid of the dy and the dx, okay? So in a way, they're gonna cancel each other, okay? So what is the integral of y to the -3? Well, we know that that's actually, well, I'll write it out. So this is y to the -3 dy, and this is the integral of x to the -1 dx, okay? So if I bring this over here, this is going to be add 1 to the power and then divide by it. It's our general power rule. So I'm going to say y to the -2 divided by -2, okay? And then we're going to have that equal to the integral of x to the -1 is the absolute value, I'm sorry, the natural log of the absolute value of x plus c. Now, technically, isn't there two c's? Isn't there one on the left side for the plus c there and then one on the right side for the plus c there? But when you take that one plus c plus the other plus c, you get some new c. So let's just call it plus the c, okay? So some new constant, okay? So now let's clean this up a little bit. This is -1 over 2y squared. That's pretty ugly. Let me write that better. ln of the absolute value of x plus c. Okay, now my job in general, so for the general rule is if you can solve for y, you do it, okay? So in this particular problem, I have to solve for y because I can. There are some instances that it's nearly impossible to solve for y, so you can just leave it in the form that you're presented with. So sometimes, like how we have it right here, that would just be your answer, okay? But in this case, I actually can solve for y, so I'm gonna flip this. And I'm going to multiply, let's see here, y over to the other side, y squared, and I'm going to divide. So this is going to become -1 over ln of the absolute value of x plus c. So basically, this is what I did, guys. I just divided the whole thing, right? And then I multiplied y squared over to the other side. Okay, so that cancels that. That's a 1. That's a 1. So now let's see what we have left. So we have -1 over ln of the absolute value of x plus c. Absolute value of x plus c equals y squared. Then you guys know that we have to cancel that with that. Inverse operations. So now we're left with plus or minus the square root of -1 over ln of the absolute value of x plus c is equal to y. We have our solution to our differential equation. So in general, if you can solve for y, you do it. Now, some of you might be freaking out because of this -1, but remember, you don't really know what c is. So maybe c is some really big negative. So then the ln of x minus c will be negative, and a negative over a negative is a positive. So this is very possibly the answer, okay? So this is our first separable differential equation that we solved. Okay, so let's take a look at another one. So, and again, I know it's not, this isn't like super easy, but I feel like it's concrete. It's much more concrete than sequences and series and what we were dealing with, you know, the comparison tests and everything like that. Okay, so let's look at another one. Oh boy, this is a really tough one. You know what, this video is already going longer. I don't think I have another 10 or 15 minutes in me, so I'm going to send you guys this video, and then we'll talk about the next, we'll pick up with 9.3 and finish it off in the next video. Okay, you guys, thanks for your time, and I will talk to you soon.